Alright, wanted to do a quick review of the graph paper and get you through reading a sinus rhythm here. So what I have is a little snippet worth of graph paper, and if you look on here, I've got the brush size set kind of big, so it's going to over obscure these lines if I do this right. But right here, what I have is a 5 by 5 grid, and if you remember, each one of these little dots, the dot to dot here from this space over to this space, so for example from right here over to right there is 1 millimeter across, from there to there is 1 millimeter down, from there to there is 1 millimeter back, and 1 millimeter up. So essentially that small section in here, this is a 1 millimeter by 1 millimeter square. The larger sections out here are a 5 by 5 grid of those. So it's 5 millimeters by 5 millimeters. And if we do just a little bit of review here real quick, if you remember, the standard for graph paper is that it should move at 25 millimeters per second. And what that resulted in, if you divide 25 into 1 second, you get 1 millimeter. So that little tiny box, the left to right component of that, is equal to 0.04 seconds, which is also 40 millisecond. And if you go with the 5 boxes, a 5 millimeter, going once again left to right, gives us 0.20 seconds, which is also equal to 200 milliseconds. And if you remember our vertical axis on here, the y-axis, so the up-down component, so if I did this, here I'm looking at left to right, here I want to look at up and down, so I have 1 millimeter is equal to 0.1 millivolts, which means logically that 5 millimeters is equal to 0.5 millivolts. And quite logically, 10 millimeters is a 1.0 millivolt. I tend to put these zeros before and after the decimal point just because it helps those decimal points stand out a little better. But essentially it's 0.1 millivolt per millimeter, 0.5 millivolts per large block, and 10 millimeters or 2 large blocks would be 1 millivolt. And another thing that we haven't really talked about is what's called a standardization mark. I'm going to change color here for just a second, and we'll do this over in blue. But if I were to draw on this particular graph, a standardization mark here would be something that comes across like this and goes up for 2 blocks, exactly 2 blocks, cuts over, comes back down, and we've got a flat piece. So a standardization mark, if the paper is running at 25 millimeters per second, it will be 0.20 seconds. So if I write that out, standardization mark, the purpose of a standardization mark here is essentially to allow the paper to, the actual printing to determine what the paper size is. So it will be 1 millivolt tall and 0.20 seconds wide. And I talked about this very briefly in class, but essentially if I have something that comes across like this and it's up, it's twice as tall as it is, and it's 2 blocks tall, 1 block wide, large blocks I'm talking here, then it's running at normal speed. If I have one that looked like this, well, what that means to me is that we've actually cut our voltage in half. We maybe have something that's really showing up as high voltage, so it's only 1 block tall and 1 block wide. That means that the voltage is showing half as tall. So this would be 1 millivolt. Likewise, if I had one that looked like this, where it's as wide as it is tall, that line back over there, then what we're doing is we're kind of running that time-lapse photography, that really high-speed paper. We're running this at 50 millimeters per second. So the paper will also print that and show it, but the standardization marks are still out there, so if you run into them, at least you know what you're looking at. Next thing that I wanted to do, we'll clear that, is show you what a 6-second strip worth of paper is. Now, if I go through and count this out, I'll just do this to kind of save some time. I'll tell you what, let's get back to red here so it stands out a little bit. And I'm just going to draw some marks across here as I go. This is probably going to be a little sloppy, so bear with me. But there's... have to be smarter than the machine. Sorry, guys. Okay, so come back over here. There's 1 block, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and if you notice right here, 15, there's a hash mark. So there's a hash mark at the beginning, there's another hash mark over here. That's a 3-second segment, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So this ends up being a 6-second strip. Your paper's going by at 25 millimeters per second. So if we did a little math here, 25 millimeters per second times 60 seconds came up with 300. And that was one of our charts that we made another day to determine rates. And if I want to take a tenth of that, make it a 6-second strip, 25 times 6 times 6 there is just 30. So I went with 30 large blocks moving across here. That's a 6-second strip, and that's typically what you're going to see when you're looking at EKGs. Remember these blocks down here, you've got each large square box is 0.2 seconds wide and 0.5 millivolts tall. If we had a standardization mark out here at the beginning, I'd have one that would come across here, and it would go up 2 blocks, hopefully, cut across, come right back down, and then we'd move into our rhythm and so forth. So I'm not going to get into my chicken scratch on here just yet. I just wanted to show you essentially how the graph paper is laid out on here. So we'll take that off, and I'm going to switch over here now. This is a small snippet of a rhythm. Well, first thing we can do is we can take a look over here, and I can see it's very tiny. Probably doesn't show up real well on your screen, but there happens to be a little tiny hash mark above the line there. And if I come over here right to the middle, there's another one, and at the end. So what I have here is this part is 3 seconds, and this part is 3 seconds. So the whole mess here is 6 seconds. And what that essentially tells me is that I have a 6-second strip. It's going to be 1/10 of a minute. So I can count the QRSs and multiply by 10 and get our rate. And if I start counting out here, first thing I want to do is take a look at the QRS. Well, one of the magics of computers is I'm going to zoom in, and I'm actually zooming in on this central beat here. So if I pull that up, I'm going to look at my QRS. Now remember, the QRS is a big, tall, up, down, spiky, pointy thing, and just to kind of save some space here, I didn't show the entire height of this. But I'm going to start right here. So this line pretty much right down here, and actually I need to put it on the right layer. So pardon my clicking around here. But right here is where that QRS starts. And right over here, well, actually that's kind of sloppy. Let's do that better. Right there is where the QRS ends. So if I do this, the line is kind of buried in there, but from here to here, that would be 1 block, And from here to here, that would be 2 blocks. So my QRS is actually 2 small blocks wide. And if you remember, each small block is equal to 0.04 seconds. So if I come back over here and I want to start writing this down, I can say my QRS is equal to 0.08 seconds. And this is going to go behind there, but you'll see it in a second. So 0.08 seconds, and I have, it would be 2 small blocks. Alright, then the next thing that I want to do is I want to look for P waves. Well, to look at the P waves, we can just look in general here. And let's do the P waves in a different color, so I'll grab green, and I can go ahead and mark these off. So there's a P wave there, P wave there, P wave, P wave, and P wave. So my P waves, then I want to look at their shape. The shape is round, they're upright, and they're symmetric. And that's what they need to be. So I'm going to say P wave is round, upright, and symmetric. And if you remember here, upright is critical. The round and symmetric is nice, but the upright is absolutely critical. So we've got P waves are round, upright, and symmetric. And if I go back over to here to red for just a second, I can mark off on here. Oops. There we go. I can come back up here and say, there's a QRS, there's a QRS, 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 QRS. So these are all evenly matched out. So my PR ratio, and I'll keep this in red just for now, PR ratio is equal to 1 to 1. Every time I have a P wave, I have a QRS. Every time I have a QRS, I have a P wave. And finally, for PR, well, not finally yet, but I need to go back to my PR interval. So my PR interval, I'm going to do this in purple. I already have this red line. We decided where the beginning of the QRS is. So the beginning of the QRS is kind of right there, and the beginning of my P wave is right here. So this starts just after the line. So moving over to here, that would be 1 block. Over to here would be 2. Over to here would be 3, and it's just a tiny bit more than 3. So what I'm going to do is say PR interval is equal to 3. Oh, I'm running out of screen, or out of my space here, so sorry, that's up there. 3.2 blocks, which if we did the math on there, 3 blocks would be 0.12 seconds, and then another fifth of that, and end up being like 0.13 seconds. So 0.13 seconds. And if you remember, that falls within the range that we need. So let's, get this clutter out of the way, and I should have wrote that in the right spot. I'll tell you what, it's a good excuse for me to come back over here, and we'll write PR interval up here. Interval. .13 seconds. And since we're measuring this, I'm going to make my pen just a little bit smaller here. Let me go ahead and mark off on this. And we'll pick on this one just because it happens to be there. So if I go from here, remember I'm going from the beginning of the P wave to the beginning of the Q wave in this case. So this thing right there is my PR interval, And I guess just kind of help clarify that. Get a little bigger brush now. Once again. Oops. There we go. And if I can get my pen back, there we go. I want to just mark where that is. So there's my PR interval. And that seems consistent, so I've got the same distance each time. Last thing I want to do is measure my R to R interval. So R to R interval, one way that I can do it, and I'll use that for this purpose, is to go ahead and count blocks. And we'll do that here in kind of a weird orange color. So if I count blocks, I'm just going to go by large blocks for now. I've got 1, 2, 3, 4, 5.5. So this is 5.5 large blocks. Count over there, there's 1 to the middle, 2, 3, 4, 5.5. Come over here just after the line, 1, 2, 3, 4, 5.5. And again, just before the line, 1, 2, 3, 4, 5.5 once again. So everything lines up nice and even. And I have 5.5 blocks each. So I can come back over here and say my R to R is regular. Now, if you remember QRS being narrow, I can throw a little check mark there. P waves are round, they had to be upright and symmetric. PR ratios 1 to 1. PR interval happens to be between 120 and 200 milliseconds, or 0.12 to 0.20 seconds, and my R to R is regular. So all these characteristics meet with a sinus rhythm. Then I count the number of beats that occurred here, and I can just count my red marks here. So I've got 1, 2, 3, 4, 5 that happened within a 6-second strip, and I have my rate. And I'll tell you what, we're going to use this symbol because it's approximately, it's not going to be exact, but my rate is approximately 5 on that strip, so you multiply it by 10 to get the final rate. Whenever you give me a rate, give me the rate in beats per minute, not beats per 6-second strip. So my heart rate here is 50, and as you know, that's kind of a slow rate. So what we have after we've completed our analysis on all this is that this rhythm is classified as sinus. If you remember, the slow term was Brady. And cardia. And that's the basics of how to read a single rhythm.